Welcome to the video 4b in the thermodynamics. This is about the temperature dependence of the saturation pressure. We can find this in the textbook at page 201, and it is the deduction of the Clapeyron equation. This is about equilibrium at two conditions. Close to each other. We now have two flasks. And we have vapor and liquid in both of them. We have a temperature, we have a pressure, we have Gibbs free energy in the liquid, and we have a Gibbs free energy in the vapor. The conditions here is T plus dt. It is T saturation plus dP. We have a GV plus dGV. So we have one bottle as at this T and P conditions, and another flask with a slightly higher temperature and a slightly higher pressure. And then dGV must equal dGL. So if we change, we know that GV must be equal to GL here, and we know that GL plus DGL. Here, the new Gibbs free energy in the liquid must also be equal to the new Gibbs free energy in the vapor. So minus SVGT plus V dP equals minus SL dt plus VL dP. And from that, V minus VL dP is equal to SV minus SL dt. This is the volume change of vaporization. So this is delta V of vaporization. The change in entropy from vapor to liquid must be the change of entropy, delta S of vaporization. And the change in entropy of vaporization is the change of entropy divided by T. And then if we rearrange this, we have the change in the saturation pressure with T must be equal to delta H of vaporization divided by T and delta V of vaporization. This is the Laplace equation. I think Laplace was French. I don't know more about him. And this is exact. We start with two conditions very close to each other, and then we just use basic thermodynamics equations to deduce this Laplace equation. Then I will go on to the Clausius Laplace equation. Then we assume that ideal gas law is valid and that the volume in the vapor is much larger than the volume in the liquid, or the molar volume of the vapor is much larger than the molar volume in the liquid. Then, if we use that one, we have that V saturation over P equals, no, we take, no, we continue on that, equals delta H VAP dt divided by R T squared. What I could put directly in from here is that dp sat dt equals delta H VAP over T times RTP. If we take that one and insert the volume on vaporization, we take that one, and then we turn that into that expression. And then we just change that one slightly to d ln d saturation equals minus delta H of vaporization over R d1 over T. And this is the Clapeyron equation. What this means is that if the heat of vaporization is known, and the saturation pressure is known for a temperature like T1, then the saturation pressure can be calculated for another temperature T2. If we integrate this equation from a reference pressure to a saturation pressure, we can put this outside, and we have to integrate the temperature from the saturation temperature to T. And then we end up with the logarithm of the ratios of the saturation pressure for a given condition to a reference condition, which is this constant times 1 over T minus 1 over reference temperature. So this is a useful equation to estimate the saturation pressure as a function of temperature if P sat is known for one temperature. So, what I have done is that I have deduced one exact relation between the saturation pressure and temperature based on some assumptions I have made or found another equation which gives the relationship between the saturation pressure and the temperature. And again, from that it is possible to deduce a simple equation, or at least an equation that is useful to find the saturation pressure for a new temperature if we have the saturation pressure for a reference temperature. So that is the end of video 14.